A student carried out an experiment to find the temperature rise for a reaction between hydrochloric acid and sodium hydroxide. Student used a measuring cylinder to place 50 centimetres cubed of 0.4 molar hydrochloric acid in a glass beaker. So used a glass beaker. They put the 50 centimetres cubed of HCl in there. Student recorded the temperature at 1 minute intervals for 3 minutes. At the 4th minute, the student added another 50, and this was of NaOH. Stirred but didn't record the temperature. So the 4th minute is where we're doing our addition. And they kept recording the temperature for a further 8 minutes. Plot a graph on the grid opposite. So we're going on to the next page and we have to plot a graph. So I'm just going to have to turn the page so that I can fit this in. And then we're going to look at this graph that the paper they've given us. Remembering that the shape of this graph, we're going to have time along the bottom axes. Remember that the exam board, they pretty much always give you the right amount of paper. So if this is how much they've given us, then this is probably what we need for time. And our time is in minutes. And we need to go up to 12. So let's have a look. Does it go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They pretty much always give you what you need. Now we need to get up to our 6th temperature of 21.7. But remembering that in this graph, we do end up having to extrapolate backwards. So it may go higher than 21.7. So do think about what the graph is going to be like. This is an enthalpy graph, and this is the one with the 2 lines, and you extrapolate to the point of addition. It looks like it's steady at the beginning. So I'm actually going to start my graph at 19.8. And I'm going to try to get to about 21.8, 21.9 in case I need to go back up a bit higher. 9, 10... So that would be 20, 20.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think we're going up in 0.1. So 19.9, 20.0, 20.1, 20.2, 20.3, 20.4, 20.5, 20.6, 20.7. You have to use as much of the paper as you can. And remember that the exam board, they do always try to give you the right amount of paper for the graph to really spread the data out. So for the first 3 minutes, it was just exactly at 19.8. And so that line is going to get extrapolated along the bottom of the axes. Then at the 5th minute, we've got 21.4. Then 21.7. Then 21.6. 21.5. 4. 3. So very steady rate of cooling here. So we're going to take our ruler. And we're going to extrapolate the rate of cooling back to the 4th minute. Do remember that that first point is not included because it was still warming up. So we're going to extrapolate back to the 4th minute, 5th, 4th. I'm just going to get rid of it a little bit. So about there. And then I'm going to join these 2 lines together. In order to read my temperature rise, which is 21.9 minus 19.8, which is 2.1 degrees C. I'll just turn my iPad back now and scroll back to where we were. I got 2.1. Now there are 5 marks here. First mark is for did you put, and I don't think I actually labelled in the end, so did you put your temperature on the y-axis and your time on the x, and did you use a sensible scale? You need to have used at least 20 little squares, so I'll just draw this on here and then rub it out. 20 little squares would be these 4 big squares to represent 1 degree C. So you could have done it a little bit smaller than I've done it, but that needed to represent at least 1 degree C and no smaller than that. Did you plot the points correctly within half a square? Did you draw 2 lines of best fit between 0 and 3 and 6 and 12? Did you extrapolate to the 4th minute, and did you work out your temperature rise? It then says the uncertainty in each of the temperature readings was 0.1. Now we took 2 temperature readings to get our temperature rise value of 2.1. If you didn't quite get 2.1, you would have to put your value down at the bottom here. This comes out to be 9.5%. Suggest a change to what they wrote that would minimise heat loss. Now they used a glass beaker, so we wanted to replace the glass beaker with a polystyrene cup. You could also talk about insulating the glass beaker using a lid, something like that. Suggest and explain another change in the experiment that would decrease the uncertainty in the use of the same thermometer. So remembering that it was the uncertainty over the reading times 100%, and we can't change the uncertainty because we can't change the thermometer. If we want to make this value smaller, then we will need to make the reading bigger. So how could we make the reading bigger? We want to get the temperature rise bigger, and the only way to do that would be to increase the concentration of the acid or alkali. Now we can't increase the amount of acid or alkali, because if we increase the volume, the temperature rise would actually get smaller because there's more water to heat. So we want to increase the size of the temperature rise, the magnitude, and we do that by increasing the concentration of the acid and or the alkali. One, the other, both, it doesn't matter. A student then completed another experiment to determine the enthalpy of neutralization of ethane dioic acid. So diprotic acid, it's got 2, and it wants us to react it with KOH. Well, it's got 2 acidic protons. If you have a look, there's one here and one here. And so you will need 2 KOHs to neutralise that, one for each proton. The assault is when the H+ ion of the acid is replaced by a metal or an ammonium ion. So this will be our balanced equation. The student adds 25 centimetres cubed of the ethane dioic acid. Let's work out how much that is. 25 centimetres cubed of 0.8 molar. So if we work that out, then we can see that that is 0.02 moles, and it was to 75 centimetres cubed of 0.6, that'll be 0.045. Okay, but if we look at it said the temperature, so the delta T is 3.2. And it wants us to calculate the enthalpy change per mole of water. So we need to know the number of moles of water. But we need to be careful because we've got different moles of starting materials, and we need to find out who's limiting the amount of water we make. So each HC, like ethane dioic acid, needs 2 KOHs. So 0.02 needs 0.04, which means this is limiting. There's more KOH than there is acid, which means that we're going to limit our reaction by the acid, which means the moles of water will be found from the moles of acid, and the moles of water is 2 times the moles of the ethane dioic acid from the balanced equation. So it's 0.04. Okay, so that's going to be the moles we use in the delta H calculation. We're going to need to find the energy Q first. So the mass of the solution was, in total we'd put 75 and 25, so 100. 4.18, oh no, it's telling us to use 4.2. And 3.2 was our temperature rise. So you type that in your calculator. This will give you an answer in joules. And then delta H in kilojoules per mole. So I want to turn my joules number into kilojoules and divide by my moles of water, which I worked out was 0.04. And I've typed that in my calculator and I'm going to get 33.6 kilojoules per mole. But remember that the temperature rose, so I now need to insert the minus sign to show it's exothermic. And let's just check if we needed specific significant figures, which it doesn't ask for. So I'm going to stick to my 3 minus 33.6. And then the final part of this question, they did the same reaction between sulfuric acid, which is also a diprotic acid, and KOH. So we get K2SO4 and 2H2O. So balancing's the same. Found it was minus 57, so more energy released. Why is there a different value? Well, the first thing to realise is that ethane dioic acid is a weak acid. H2SO4 is. So the difference between those is that the H2SO4 is fully dissociated, but the ethane dioic acid is only partially dissociated. And the point then is that energy is needed put in to dissociate the ethane dioic acid before neutralization. So the strong acid is already fully ionized, so the value to go from my H plus and my OH minus down, because it was already fully dissociated, is just the minus 57 it says for sulfuric acid. But here I've got my weak acid and I need to put energy in to break up my weak acid and dissociate it before it can come down. The resulting of that is that we haven't actually got as much down energy released. It was only our minus 33.6. So we didn't quite get as much energy released because we had to put energy in first.